In this video, I will be deriving the formulas that you use to find the equivalent resistance in series and parallel circuits. Maybe you've already used these before, but never received an explanation of where they come from. All you need to derive these equations are the conservation of charge, the conservation of energy, and the definition of resistance. So if you've got all that, you're ready to go. Let's start with series circuits. Consider a circuit with a cell of voltage V generating a current I connected in series to two resistors R1 and R2. By the conservation of charge, we know that the current around the circuit must be the same, since there's nowhere for the charge to go but through the wire. So both of them have a current I as well. By the conservation of energy, we don't necessarily know that the voltage in each resistor is the same, but we do know that the potential difference across the two resistors needs to add up to the potential difference across the cell. So let's convert all that information into mathematics. So we know that the potential difference across the resistors adds to the potential difference across the cell. That as an equation, you can just write that as V1 plus V2 equals V. We also know by the definition of resistance that the potential difference across a resistor is IR. So we can substitute IR into our conservation of energy equation. We get that IREQ, resistance equivalent, or equivalent resistance, is equal to IR1 plus IR2, and realizing that the current is a constant factor on both sides, we can cancel out the i's. And that's the equation for the resistance in a series circuit. The process for a parallel circuit is actually pretty similar, so if you want to pause and try now, I'd definitely encourage that. In any case, here's what you would do. Once again, consider a cell of voltage V generating a current I connected to two resistors, but this time in parallel. By the conservation of charge, we don't know if the current in the two paths is the same, but we do know that it must add up to the current from the cell. The potential difference across each resistor is actually equal to the potential difference across the cell. Maybe this isn't totally obvious, but it can be understood intuitively by considering the definition of potential difference, work done per unit charge. So another unit for potential difference is joules per coulomb. Using that information, imagine two electrons on their trip around the circuit. The cell has given them both some energy, so when they split paths, each resistor still receives the same number of joules per coulomb of charge. And so they receive the same voltage. Alright, so let's turn these insights into mathematics. By the conservation of charge, the current is equal to I1 plus I2. Then by the definition of resistance, the current across a resistor equals the potential difference across it divided by its resistance. So we can substitute that into our conservation of charge equation. Then, because V is a constant factor, we can cancel that on both sides, and we're left with the equivalent resistance formula for a parallel circuit. So that's it. Hopefully that was helpful, but if you have any questions, leave them in the comments, and feel free to watch some of my other videos. Thanks for watching, and bye-bye.